Welcome back. We are going to be talking about the preparation of carboxylic acids. We've already learned 3 different ways to make carboxylic acids, and I'll show you 2 new ways today that kind of piggyback on things we've seen already, okay? So in section 10.9, we've learned that alkynes can be ozonolized to produce 2 carboxylic acids, the same if we have a symmetrical alkyne. So for example, if we have a molecule that looks like this, okay, we can treat this with ozone and then treatment with water. Okay, don't forget the water as a second step here. And what this is going to produce are 2 carboxylic acids. Now, the carboxylic acids are going to be completely identical because this molecule has a plane of symmetry down the molecule. So I'll just put a 2 in front of this so you can see that there's 2 molecules here produced. So these 4 carbons come from the carbons that are on the alkyne. So the alkyne carbon becomes the carboxylic acid carbon, okay? In section 13.10, we learned about the Jones oxidation of primary alcohols. So remember, it's only primary alcohols that can be oxidized to produce carboxylic acids. So for example, if we have something like this, this is a primary alcohol because there's 2 hydrogens on this carbon atom here. And if we treat this with sodium dichromate, sulfuric acid, and H2O, which I just call the Jones reagent, okay, you will make a carboxylic acid with the same branching and pattern and same number of carbons, okay? So just oxidation. The third way that we can produce a carboxylic acid is by a side chain oxidation. So if we have something like this, okay, the magic here is that we have a benzylic hydrogen, right? There's hydrogens attached to the benzylic carbon, and we can oxidize that through many different ways. I just suggest you memorize potassium permanganate. Jones reagent is also a possibility. And so this will make a benzoic acid derivative, okay? So that's very specific for the alkyl groups attached to the benzene ring or the phenyl ring, okay? You can't just do that on any methyl group you like, all right? That's going to be a different reaction. Now, 2 new ways to do the synthesis of carboxylic acids is, so here's reaction number 1 new. This is hydrolysis of nitriles. Now, nitriles don't even contain an oxygen in many cases, but we do consider them to be carboxylic acid derivatives. Now, if you look at this carbon atom here, that's going to change into the carbon of the carboxylic acid. These reactions take a while. I've personally done these reactions, and they require a very concentrated acid, like 8 molar sulfuric acid, and you set it up a reflux overnight, and you come back the next day, and hopefully it's complete. Okay, so it's 16 hours, something like that. Boiling sulfuric acid. So we have H3O plus. And don't forget the heat. Okay, you definitely need a triangle that represents heat under the reaction arrow. And this is going to make, I'll draw out that C so you can see it's still there, this carboxylic acid. Okay, now nitriles are not very common, so remember that those come by an SN2 reaction. So usually this is a 2-step sequence. If you have an alkyl halide, you would normally treat this with sodium cyanide, okay? And, you know, some polar A product solvent, doesn't matter here really what we write. And I'm highlighting this in green so that you can see we're growing the carbon chain by one carbon. You see, cyanide contains a carbon, and it's actually added to the molecule now, all right? So here I have a molecule with only 4 carbons, and here I have a molecule with 5 carbons, and so that's going to make a carboxylic acid that has a total of 5 carbons. And I'll draw that in, I don't know, green, I guess. So here's my carboxylic acid that I've introduced. So if you look at the net change here, we're changing this halogen, chlorine or bromine or iodine's the best leaving group, right, for a CO2H group, okay? So that's the overall sequence of events. You know, how do we go from something like this to something like this? We have to do 2 steps. Step 1, sodium cyanide. Step 2, H3O plus and heat. All right? So I'll write that down here. Now remember that when you treat an alkyl halide with sodium cyanide, that goes through an SN2 reaction mechanism, and this won't work on tertiary or vinyl or aromatic halides, okay? So if you have something like this, and you treat this with sodium cyanide, there's no reaction, okay? The reason why is because there's no SN2 on sp2, okay? The sp2 hybridized carbon here is not geometrically predisposed for an SN2 type, you know, transition state. And if you have a tertiary alkyl halide and you treat this with sodium cyanide, okay, you also are not going to get a reaction occurring because there's too much sterics, okay, for the cyanide to kick off that halogen, okay? So there's no SN2 on tertiary carbons, okay? So these are the 2 things from chapter, whatever these, at the SN2 chapter. I don't remember which chapter that is, okay? Now, the second way to produce carboxylic acids is by a Grignard route, okay? So if we have a Grignard, okay, this has a total of 3 carbons, and we treat this with carbon dioxide, okay? And then we treat this with a little bit of acid. We will make a carboxylic acid in a very similar fashion with 1 additional carbon. So we started with 3 carbons, and now we end up with 4 carbons. Where did that carbon come from? It came from the carbon in the carbon dioxide, okay? So how does this work? Okay, so first of all, remember that your Grignards are carbanions. There's a carbon atom with a lone pair, a negative charge. We'll fill in the 2 other groups there. This carbon does not have 4 bonds, okay? So, but it is a carbanion, it is nucleophilic, and it can attack carbon dioxide. So you can think of carbon dioxide as kind of having a carbonyl, like an aldehyde or a ketone. And so these electrons here will attack the carbon, and electrons will swoop to the more electronegative element, and you'll form a carbon-carbon bond, okay? And what you form is a carboxylate. Okay, that's a carboxylate. We've already learned about that in section 2, just the previous lecture. And so if we add that to H3O plus, there's a protonation event to give you the neutral carboxylic acid from that. Okay, so in the first step, you have attack, and in the second step, you have protonation. okay? So AP for short. There is absolutely no limitation whatsoever on this reaction. So for example, let's say I have this meta-bromoethyl benzene. I can treat this with magnesium in diethyl ether, and that will give me the green yard that I need. Okay? And I can treat this with CO2. Okay. Usually, quite literally, you grind up some dry ice and you add the powdered dry ice to your reaction, and it just bubbles away and so on. But it reacts very quickly with the green yard reagent. And then you slowly add, acid until you get a neutral pH or so. And so this will give you the carboxylic acid. So keep in mind that you have an extra carbon here, okay? So that's the carbon of this that came from the carbon dioxide, okay? So that would work great for an aromatic compound. There's no problem there. It can also work for a tertiary alkyl halide. So for example, if I had this molecule here, which is 1-chloro, 1-methyl cyclohexane, I can treat this with magnesium in diethyl ether, okay? I can treat this with carbon dioxide, and I can treat it then with acidic water or something like this, and that will make 1-methyl cyclohexane carboxylic acid. Okay, 1-methyl cyclohexane carboxylic acid. So that's a great little synthesis. Okay, so the first step is the first way of doing that is through something called hydrolysis of nitriles, and the second way of doing that is just by using green yards. Green yards and CO2. Okay. Okay, in problem 21.10, this is a little bit about reviewing what we've seen. There's 5 different reactions to produce carboxylic acids. So going from ethanol to acetic acid involves Jones reagent, and you just need to put that on a note card and just kind of keep it in your back pocket and review that 4 or 5 times a day, okay? And your stack of note cards is going to be quite big. You might have to put it in a backpack after a while. In reaction B, we want to go from toluene to benzoic acid. Okay. Benzoic acid is a carboxylic acid, so this is a benzoic situation. So all we need to do is add, just write KMNO4 above the reaction arrow. Okay. There's a whole bunch of other stuff and refluxing and workup and all that, but just write KMNO4. Okay. How do we go from benzene to benzoic acid? There are several different ways of doing this. I'm just going to treat this with chloromethane with a catalyst called aluminum trichloride to give you toluene, and then I'm just going to use potassium permanganate. Okay, I could brominate and then do the green yard and the CO2 and all that, but that's 3 steps. Okay. In D, I want to go from 1-bromobutane to pentanoic acid. This would be a good opportunity to use the green yard route, but I don't know, I'll just use sodium cyanide just so you can see that, okay? Count your carbons and be careful. If your carbons are increasing by 1, you need to introduce a carbon. It could be cyanide. This is a primary alkyl halide, so that will react quite readily with sodium cyanide. And if I add acidic water to this, it'll neutralize the solution and form the pentanoic acid. Ethyl benzene to benzoic acid. So again, remember that if you have a benzylic hydrogen, you can blast this molecule with potassium permanganate and it'll remove all of the other carbons. What ends up with, where does that carbon go? It's carbon dioxide. So if you really want, you could write minus CO2 on the bottom. That gets, evaporated or leaves the reaction flask. Okay. The next one, we have bromocyclohexane going to cyclohexane carboxylic acid. Whoops, that's not cyclohexane, that's a phenyl ring. Okay, so how do I do this? Well, this is a secondary alkyl halide, so you could use sodium cyanide, that would work well, or you could do the Grignard route. We don't have Grignard as an answer here yet, so I'll just choose the Grignard route. So I could add magnesium with diethyl ether, okay? That will create the Grignard. Now don't forget the CO2, we need to add carbon dioxide, that's our source of carbon, and then we need to add acid. Okay, so this is just a review question. I hope you kind of got a feel for this. Any one of these reactions right here on this page would make great flashcards, so please study and memorize the reagents. And that concludes the synthesis of carboxylic acids of old kind of reactions we've seen before. So now we'll get started on section 21.5 in the next video. Thanks for watching, and please consider subscribing.